The middle layer of the sun's atmosphere. Chromosphere. The chromosphere is a layer of the sun's atmosphere located above the surface, visible during solar eclipses, and it emits a reddish glow due to its hot gases. Imagine you're at a crowded party, trying to get from one side of the room to the other. Just like at a party where you have different layers of groups to navigate through, the sun's atmosphere is made up of layers. With the chromosphere being the middle one, you must pass through between the core party area and the outer entrance. The crowded party, with its distinct layers of people, is like the sun's atmosphere, where the chromosphere acts as the middle layer, separating the inner core activities, photosphere, from the outer atmosphere, corona, much like navigating groups to reach your destination. The outermost layer of the sun's atmosphere, corona. The corona is a glowing halo of hot, ionized gases surrounding the sun, visible during a solar eclipse. Imagine trying to find the right lid for a pot when you have a cluttered kitchen cabinet. Just as the outermost layer of your kitchenware can be overlooked among the chaos, the sun's corona is an elusive layer that we don't often notice amidst the bright glare of the sun itself. Just like the lid that sits on top of the pot, the corona is the outermost layer of the sun's atmosphere. And though it may seem inconsequential compared to the intense core, it plays a crucial role in the sun's energy dynamics. The process by which hydrogen atoms join together to form helium inside the sun. Nuclear fusion in the sun is when hydrogen atoms combine to create helium, releasing energy that powers the sun. Imagine trying to squeeze two very stubborn magnets together, with the same poles facing each other, as they keep pushing away from one another. This is similar to what happens in the sun, where hydrogen atoms resist each other due to their positive charges, yet under immense pressure and heat, they are forced to combine to form helium. Just as you need to apply a significant force to overcome the repulsion between the magnets, the sun's core provides the intense pressure and temperature needed to overcome the repulsive forces between hydrogen atoms, allowing nuclear fusion to occur. The surface layer of the sun that gives off light. Photosphere. The photosphere is the part of the sun we see that emits the sunlight that reaches Earth. Imagine you're trying to find the best way to present yourself for a job interview, ensuring that your appearance and demeanor create the most favorable impression. This situation is similar to how the sun's photosphere functions as its surface, radiating light and energy that we can see from Earth. Just as your outward appearance and behavior are what people perceive, the photosphere is the sun's visible layer that emits light, making it the face of the sun that we observe from our planet. A stream of electrically charged particles released by the sun's corona. Solar wind. Solar wind is the flow of charged particles from the sun that can affect space weather around Earth. Imagine you're trying to carry a large bunch of balloons on a windy day, and the wind keeps pulling them in every direction. This is similar to how the sun's corona releases a stream of electrically charged particles, known as solar wind, into space. Just as the wind tugs at your balloons, the solar wind consists of particles that are pushed away from the sun's surface into space, carrying energy and momentum, much like the wind carries your balloons. All the wavelengths or frequencies of electromagnetic radiation. Electromagnetic spectrum. The electromagnetic spectrum is the range of all types of light energy, from radio waves to gamma rays that travel through space. Imagine trying to find the right radio station while driving, with each station offering different music, news, or talk shows. This is similar to the electromagnetic spectrum, where each station represents a different wavelength or frequency of electromagnetic radiation, providing various types of information, such as visible light, radio waves, or X rays. Just as you tune your radio to match the frequency of your desired station, different devices and technologies are designed to interact with specific parts of the electromagnetic spectrum to receive or transmit the right type of information, highlighting the spectrum's diversity and utility. The brightness of a star as seen from a distance of 10 parsecs. Absolute magnitude. Absolute magnitude is a measure of how bright a star would appear if it were 10 parsecs away from Earth. Imagine you're trying to compare the loudness of songs played at different distances in a crowded street. Just like how you might struggle to gauge which song is truly louder unless you bring all the speakers to the same spot and listen from the same distance, astronomers face a similar challenge with stars. Absolute magnitude is like this standardized listening spot. It's the brightness of a star as if it were observed from a uniform distance of 10 parsecs, allowing astronomers to fairly compare the intrinsic brightness of stars without the varying effects of distance. The brightness of a star as seen from Earth apparent magnitude. Apparent magnitude is a measure of how bright a star appears to us in the sky from Earth. Imagine trying to choose the loudest person at a crowded party, where some people are shouting right next to you and others are speaking quietly from across the room. Just like the apparent loudness of someone's voice depends on their distance from you and how loudly they're actually speaking, the apparent magnitude of a star is how bright it seems from Earth, influenced by both its intrinsic brightness and how far away it is. In this analogy, the people at the party are the stars, their voices are their intrinsic brightness, and your perception of their loudness is the apparent magnitude, which helps you decide who seems loudest based on proximity and volume. A star system with two stars. Binary star. A binary star is a system where two stars orbit around a common center of mass. Imagine trying to balance two spinning plates on sticks at the same time. This task is similar to how a binary star system operates, where two stars orbit around their common center of mass, much like how you must keep both plates simultaneously spinning and balanced. Just as the plates rely on your steady hand to maintain their motion and prevent a wobble, the stars in a binary system rely on their gravitational pull to maintain a stable orbit around each other, illustrating the delicate dance of forces at play. A pattern or shape formed by a group of stars. Constellation. A constellation is a recognizable grouping of stars in the night sky that forms a pattern and is often named after mythological figures or animals. Imagine trying to assemble a jigsaw puzzle without a picture on the box to guide you. Just like how you need to focus on the shape and fit of each puzzle piece to create a coherent image, identifying a constellation involves recognizing patterns among a seemingly random scatter of stars. In both cases, the individual pieces or stars might seem unrelated at first, but when you connect them correctly, they form a meaningful picture or pattern, illustrating how we make sense of chaos by finding order within it. A graph that plots the surface temperature of stars against their absolute brightness. Hertzsprung-Russell diagram. It is a chart used by astronomers to classify stars and understand their evolution. Imagine trying to choose the best apples at a grocery store, where you have to consider both their color and size. Just like you use these two characteristics to determine which apples are the freshest and juiciest, the Hertzsprung-Russell diagram uses the surface temperature and absolute brightness of stars to determine their type and life cycle stage. In this analogy, the color of the apple corresponds to the star's surface temperature, and the size relates to the star's brightness, helping astronomers understand and categorize stars just as you would assess apples to pick the best ones. The distinct diagonal band on an HR diagram that includes 90 of all stars' main sequence. Main sequence stars are those that are in the stable phase of their life cycle, fusing hydrogen into helium in their cores. Imagine trying to organize a diverse group of people by age and height, noticing that most fit into a predictable pattern where older people are generally taller. This is similar to how stars in the universe are organized by their brightness and temperature, forming a predictable pattern known as the main sequence on the HR diagram. Just as most people fall along a diagonal trend from younger and shorter to older and taller, about 90% of stars fall along a diagonal band on the HR diagram, from hot and bright to cool and dim, illustrating a natural order in both scenarios. The apparent change in position of an object when viewed from different places. Parallax. Parallax is the way an object's position seems to shift when you look at it from different angles or locations. Imagine trying to find the perfect spot to hang a picture on a wall, and every time you move to a different part of the room, the picture seems to shift its position slightly. This is similar to the scientific concept of parallax, where the position of an object appears to change when viewed from different locations. Just as the picture seems to move because your angle of view changes, celestial objects like stars or planets appear to shift against the distant background stars as the Earth moves to different points in its orbit, allowing astronomers to measure their distances. A region in space with gravity so strong that no matter or light can escape it. A black hole is an area in space where gravity pulls so much that even light cannot get out. Imagine you're trying to leave a crowded party where the music is so loud and the crowd so dense that you can barely move or hear yourself think. This situation is similar to a black hole, where gravity is so intense that not even light can escape its pull. Just as the noise and people at the party trap you in place, the immense gravitational force of a black hole traps everything close by, making it impossible for light or matter to break free. A huge cloud of gas and dust in space where new stars form. Nebula. A nebula is a massive space cloud where stars are born. Imagine trying to clean up a cluttered room where things are scattered everywhere, but eventually you start to see the potential for something new and organized. Just like tidying up transforms a chaotic space into something functional, a nebula is a vast, chaotic cloud of gas and dust that can eventually form new stars. The scattered items in the room are like the particles in the nebula, which, when they come together in just the right way, create a new structure, much like the formation of stars from the nebula's material. A dense core composed mainly of neutrons, left behind after a supernova explosion. Neutron star. A neutron star is a supercompact object formed when a massive star's core collapses under gravity after a supernova, squeezing its mass into a small, incredibly dense ball mostly made of neutrons. Imagine trying to fit all your clothes into an overstuffed suitcase after a long vacation. Just like how you compress every piece of clothing tightly together to make it fit, a neutron star is the incredibly dense core that remains after a massive star explodes in a supernova, squeezing neutrons closely together. In both cases, you have a situation where a large volume is condensed into a much smaller space. Your suitcase is the neutron star, and the densely packed clothes are akin to the neutrons, both representing how much can be crammed into a limited space. A very young star before nuclear reactions begin at its core. Protostar. A protostar is a cloud of gas and dust in space that is gradually forming into a new star. Imagine trying to start a fire with damp wood. You have all the potential for a roaring blaze, but nothing has caught fire yet. This is similar to a protostar, which has all the ingredients for becoming a star but hasn't started nuclear fusion at its core. Just as the damp wood needs more heat to ignite, a protostar needs to reach a certain temperature and pressure in its core to kick off the nuclear reactions that will turn it into a full-fledged star. The bright explosion of a dying supergiant star. Supernova. A supernova is a powerful burst of light and energy that happens when a massive star explodes at the end of its life. Imagine you're trying to hold on to a large stack of boxes while climbing a staircase, but eventually you lose your balance, and the boxes come crashing down in a spectacular mess. This chaotic scene is similar to a supernova, where a massive supergiant star can no longer support the immense pressure of its own gravity and collapses. Just as the stack of boxes becomes unstable and falls apart, the star's core succumbs to gravitational forces, leading to a dramatic explosion that we see as a bright supernova in the sky. Sure, states that the farther away a galaxy is, the faster it is moving away as the universe expands. Hubble's law. In simple terms, Hubble's law means that the universe is expanding, with distant galaxies moving away faster than those nearby. Imagine you're at a crowded concert, trying to make your way to the exit as the show ends. The people closest to you move out slowly, while those further away seem to speed up as they find clearer paths. This scenario is much like Hubble's law, where galaxies are like the concert goers. The ones further from us, or the stage, appear to move away faster as the universe expands. Just as the distance from the stage allows people to move more freely and quickly, the greater the distance of a galaxy, the faster it seems to recede due to the stretching fabric of space itself. The very bright center of a distant galaxy, quasar. A quasar is an extremely bright and energetic object powered by a supermassive black hole at the center of a galaxy. Imagine trying to find your friend at a crowded concert when they're standing right under a bright spotlight. Just like that spotlight makes your friend easy to spot in a sea of people, a quasar is the incredibly luminous center of a distant galaxy, making it stand out in the vastness of space. The spotlight is to your friend what the quasar is to the galaxy. Both make their respective subjects visible and prominent against a crowded and chaotic background. States that the universe began with a huge explosion 13.8 billion years ago. Big Bang Theory. The Big Bang Theory explains how the universe started from an extremely hot and dense point and has been expanding ever since. Imagine you're in a crowded party where there's barely any space to move, and suddenly someone drops a tray of drinks, causing everyone to scatter in all directions. This initial explosion of movement from a single point mirrors how the universe began with the Big Bang, where everything expanded rapidly from a singular, dense state. Just like the partygoers spreading out from the center, the universe's galaxies, stars, and planets have been moving away from the original explosion point, filling up the vast cosmic space over 13.8 billion years. The electromagnetic radiation left over from the Big Bang, cosmic background radiation. It is the faint glow of light that fills the universe, a remnant from its very early stages after the Big Bang. Imagine waking up to the smell of a delicious dinner you cooked the night before. Just as the aroma lingers in your home long after the meal is finished, cosmic background radiation is like the scent that remains from the cooking of the universe during the Big Bang. The connection here is that both the smell and the radiation are remnants of an earlier event, with the aroma being the leftover evidence of your culinary creation, while the cosmic background radiation is the electromagnetic scent that fills the universe, indicating the Big Bang's occurrence billions of years ago. A massive system of stars, gases, and dust held together by gravity. A galaxy is a huge collection of stars and other matter bound together by gravity. Imagine trying to keep a group of friends together at a crowded concert where everyone is being pushed and pulled by the crowd. Just like how your friends stick close to you to avoid getting lost, a galaxy is a massive system of stars, gases, and dust, all held together by gravity, preventing them from drifting apart in the vastness of space. In this analogy, gravity acts like the bond of friendship, keeping everything, stars, gas, and dust, clustered together despite the chaotic movements around them, much like how your group stays unified amidst the concert's bustling crowd. The distance light travels in a year, 9.5 trillion kilometers, light year. A light year is a unit of distance that measures how far light travels in 1 year in space. Imagine you're planning a long road trip across the country to visit family, and you're trying to grasp just how far you need to travel. Just like planning out that enormous distance can seem daunting, understanding the concept of a light year is about comprehending a vast space that can be challenging to visualize. In both cases, you're dealing with large-scale journeys. Your road trip covers thousands of kilometers, whereas a light year covers the distance light travels in a year, 9.5 trillion kilometers. So just like your car journey is broken down into manageable parts, like hours and stops, think of a light year as breaking down the immense stretches of space into something we can wrap our minds around by considering how far light, the fastest thing in the universe, travels in the span of a year. The hot, dense core of a star left behind when its outer layers have escaped into space. White dwarf. A white dwarf is the remains of a small or medium-sized star after it has exhausted its nuclear fuel and shed its outer layers. Imagine you're cleaning out a closet, deciding to get rid of old clothes you no longer wear. Once you've discarded the excess, you're left with a neat, compact collection of just your essential items. Similarly, when a star sheds its outer layers and loses the material it no longer needs, it leaves behind a white dwarf, a dense core of what once was. Just as your streamlined closet represents the core essentials after a big cleanout, a white dwarf is the remaining core of a star, stripped down to its fundamental dense state after shedding its outer layers into space. A rapidly spinning neutron star that emits radio waves. Pulsar. A pulsar is a highly magnetized, rotating neutron star that sends out beams of radiation, which can be detected on Earth as regular pulses. Imagine you're trying to find a friend in a crowded room by looking for their flashlight beam that briefly sweeps across the room. This is similar to a pulsar, where a rapidly spinning neutron star emits beams of radio waves that sweep across the sky like a lighthouse. Just as you can only spot your friend's flashlight when it points in your direction, we can only detect a pulsar when its beam is pointed toward Earth, creating a regular pulsing signal. A group of no more than a few thousand stars, all of which are about the same age. Open cluster. An open cluster is a collection of stars that form together in the same region of space and are loosely bound by gravity. Imagine you're at a high school graduation ceremony where all the students are about the same age and have spent the last few years growing and learning together. This setting is similar to an open cluster in space, where a group of stars forms at roughly the same time from the same molecular cloud and remains relatively close together. Just as these students share a common starting point and have developed alongside each other, the stars in an open cluster are born from the same cosmic materials and have similar ages, representing a celestial graduating class traveling through the galaxy together.